The night is almost unnaturally still. A windless, open plain stretches in every direction, swallowed by darkness, broken only by the silhouettes of towering radio telescopes turning their metal faces toward the sky. Their slow, patient movements sound like distant sighs. Giant machines listening for something most people never even know exists. Above them, the universe glitters with indifferent beauty. The Milky Way spills across the sky like a pale river of dust. But these dishes aren't looking at that familiar glow, they're listening to what the eyes can't perceive. The faint static, the soft background hum, the cold radio whispers that drift across space like echoes of forgotten events. Somewhere out there, in a galaxy far beyond the reach of any human spacecraft or future mission, something is happening. Something sudden. Something violent, something fast. At first it's nothing, just empty dark, and then it arrives. A single flash of radio energy sweeps across the cosmos, racing through millions of light years of intergalactic space, slipping between clusters of galaxies, threading through whirls of dark matter, passing through cold hydrogen clouds and ancient filaments of gas. For ages it travels alone, unnoticed, crossing distances so enormous that the human mind struggles to imagine them. It has no colour, no shape, no warmth, just a pulse, an explosion contained in 1,000th of a second, and then it hits Earth. One of the giant dishes twitches, not visibly of course, but in its data stream, in its measurements, in its electronic heart. A spike. A sudden, sharp peak in the noise, so clean, so bright, so unmistakably strange. In just one heartbeat of time, the telescope receives more energy than our sun emits in days, squeezed into a millisecond. A cosmic shout disguised as a tiny whisper. Fast radio bursts, FRBS, the universe's most fleeting messages. They arrive without warning, without rhythm, without mercy for human curiosity. By the time we notice them, they're already gone, so brief that if you blink, you miss something that outranks an entire galaxy in brightness for that one instant. There is something deeply humbling about detecting an event that lasted for less time than it takes for a neuron in your brain to fire. If a human blink is slow, an FRB is glacially fast in comparison. These bursts don't just come and go. They almost don't happen at all. And yet, here they are, crossing billions of years to tap lightly on the edge of our instruments like someone knocking on a door with the tip of a finger. What does it mean, really, when the universe chooses such short sentences? When it speaks in flashes too fast for any creature to consciously perceive? When its most dramatic outbursts can be written entirely between two beats of your pulse? Maybe it says something about scale, about the way we experience time compared to the cosmos. We live in minutes, hours, years. Worlds are born and die inside stars over millions of years. But FRBS, they are cosmic events compressed so tightly that they barely qualify as moments at all. A whisper that could level a civilization if only the energy weren't spread across the vastness of space. Imagine standing there in the night next to those silent, listening giants. You wouldn't hear anything. You wouldn't feel anything. Nothing in your body would react. But thousands of light years away, millions even, a catastrophic magnetic rupture on a distant star is unfolding with unimaginable violence. And the only sign you receive is a blip in a data stream. A millisecond whisper. It's strange how the universe often hides its loudest events inside its quietest signals. It forces you to wonder how many things are happening out there right now that we will never notice, simply because they didn't happen in the precise direction our telescope happened to be facing that night. The desert stays quiet, the dishes keep listening. A soft hum rises from their machinery, almost like the earth itself is holding its breath. And you, lying in bed, maybe half asleep, maybe letting your mind wander, are joining this vigil. You're listening to what the universe mutters under its breath, before we drift deeper into these cosmic murmurs, into the history, the science, the strangeness of these flashes. If you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps the channel grow and it keeps these journeys alive. The telescopes keep turning, the stars keep burning, and somewhere in the darkness another whisper is already on its way. If you were to freeze that millisecond spike on a screen and enlarge it, stretching it until something so brief becomes long enough to examine, you'd discover that what looks like a simple blip is actually a remarkably structured message. Not a message from anyone, but a message about something. A fast radio burst, or FRB, is, at its core, exactly what it sounds like. A very fast, very bright burst of radio waves. Radio waves are just light. Light our eyes can't detect, but our instruments can. They behave like any other electromagnetic radiation. They travel at the speed of light, they carry information about where they came from, and they interact with the environment they pass through. But an FRB isn't just any radio wave. It's a tidal wave of energy condensed into a single blink. The definition astronomers use is surprisingly humble for something so extraordinary. A transient radio pulse lasting a few milliseconds or less, with a dispersion pattern indicating an extragalactic origin, which is science's very polite way of saying, we don't fully know what these things are, but dear universe, they are loud. To understand how loud, imagine this. In 1,000th of a second, an FRB releases as much energy as our sun emits in 3 days. 3 full days of sunlight, every photon, every quantum of heat, every particle, compressed into a moment so short you cannot consciously experience it. If you could somehow hold the energy of an FRB in your hands, it would be enough to vaporize you, the ground beneath you, your city and possibly your continent in an instant. But that catastrophic power becomes harmless by the time it reaches Earth because it spreads across unimaginable cosmic distances. An FRB's light has been diluted across billions of kilometers of void before it brushes the edge of our atmosphere and gently taps our antennas. That is the strange beauty of astronomy. The most violent things in the universe arrive on Earth as whispers. To understand FRBs, you have to appreciate the context in which they were discovered. In the early 2000s, radio astronomy was full of known signals, pulsars with clockwork precision, quasars spewing jets across intergalactic space, the hum of neutral hydrogen, and of course, the ever-present cosmic microwave background. Everything had a pattern, everything had a context, but FRBS, they didn't fit anywhere. When the first one, the Lorimer burst, was discovered in 2007, astronomers weren't excited at first. They were suspicious. Scientists generally don't like surprises. Surprises mean something in your telescope might be broken, but the data was too clean, too perfect, too bright. This wasn't interference from a truck engine or someone's microwave. It wasn't weather. It wasn't a glitch. It was a real signal, and it was clearly coming from beyond our galaxy. How do we know that? Because of a phenomenon called dispersion. Picture a runner sprinting across the universe, but his shoes, different colours, run at slightly different speeds. Radio waves behave similarly. The higher frequencies travel through cosmic plasma faster than lower frequencies. So by the time the FRB reaches Earth, the higher pitched parts of the signal arrive first, the lower frequencies arrive milliseconds later, and the entire pulse becomes smeared out into a tiny, beautiful downward sweep. That sweep is the FRB's fingerprint. From it, scientists can measure the dispersion measure dm, essentially the total number of free electrons the signal passed through on its journey. The dm is like a cosmic odometer. The larger the value, the farther the FRB travelled. And the values were enormous. Far too large for anything inside the Milky Way. Which meant one thing. These bursts were originating from distant galaxies. Let that sink in. Not nearby stars, not local phenomena, not something in orbit or in the solar system. but galaxies millions or even billions of light years away. This alone makes FRBs extraordinary. To be detectable from that far, they must be unfathomably powerful at their source. No ordinary event, no radio flare from a star, no hum from a pulsar could explain it. Only the universe's most extreme environments are capable of this level of energy. FRBs are also astonishingly bright. If one occurred inside the Milky Way, bright enough to be comparable to the weaker extragalactic ones, it would likely overload radio receivers. If one occurred within a few light years of Earth, well, you'd definitely know about it, or you wouldn't, because your electronics would be fried before you could say, "That seems bad." But FRBs don't happen nearby, at least as far as we know. Their extragalactic origin is one of their defining traits. Everyone we've detected seems to come from a place where stars live crowded, fast-burning lives. Galaxies with intense star formation, chaotic magnetic fields, and objects pushed to their physical limits. We now know they come in different flavours, repeating and non-repeating, bright and faint, wideband and narrowband. But at this stage of the story, discovering what they even are, the shock was simple. Something out there was sending millisecond bursts of unimaginable power toward us, and each burst was a clue. A puzzle piece, a voice we didn't yet understand. For now, it was enough to know that the universe was whispering. And humanity had finally learned to listen. Long before the term fast radio burst existed, before scientists knew these cosmic flashes were common, before we had catalogues and databases and thousands of detections, there was a single moment buried in a pile of old observations, a moment no one noticed for 6 years. It was 2001. The Parkes Observatory in Australia, one of the great workhorses of radio astronomy, was sweeping the sky with its 64-metre dish, quietly recording more hours of data than any team could examine. In real-time, terabytes of signals were archived, labelled, and filed away like books no one had opened yet. And hidden inside one of those digital pages was a single pulse, a flash that lasted less than 5/10,000ths of a second. A soundless snap of radio light from far outside the Milky Way. No one saw it. For years, no one even knew it was there. The discovery came later, in 2007, when Duncan Lorimer, a pulsar specialist at West Virginia University, asked one of his undergraduate students, a 20-year-old named David Narkovich, to search through old Parkes data for interesting signals. They were hoping to find a new pulsar, or maybe a strange glitch in a known one. Pulsars, after all, are predictable creatures. Their rhythms make them ideal training grounds for students. But Narkovich didn't find a rhythm. He found something impossible. A single pulse, bright enough to stand out instantly, even in raw, noisy data. It didn't repeat. It didn't resemble interference. It had the sharp, clean profile of an astrophysical event. And when they measured the dispersion, the cosmic delay between high and low frequencies, they saw something astonishing. The signal had travelled far, far beyond the boundaries of the Milky Way. It was like opening a dated notebook and finding a message clearly addressed to you, yet written before you ever knew it existed. When Lorimer saw the data, he didn't get excited. He got suspicious. Astronomers are trained skeptics. If you see something extraordinary, the first question you ask is, what did we do wrong? Hardware glitch, local interference, airplane, satellite, faulty cable, a grad student microwaving a burrito near the dish, a surprisingly non-hypothetical issue, as later events would prove. But this pulse, now called the Lorimer burst, was too clean, too strong, too bright. A pulse that, powerful at that distance, implied an event that defied the usual astrophysical playbook. If it truly came from another galaxy, then whatever produced it had unleashed more energy in a blink than most stars emit in weeks. The scientific community's reaction, a mixture of fascination, disbelief, and raised eyebrows. Some astronomers were intrigued. Others were openly skeptical. One bright, lonely event in a sea of static wasn't enough to rewrite textbooks. Some suspected an instrument artifact, some an unknown form of interference. After all, Parkes had a history of picking up odd signals. The idea that the telescope had captured a genuine millisecond flash from a distant galaxy felt dramatic. Lorimer and his colleagues published their findings in Science in November 2007, cautiously proposing that the burst might have been the result of a cataclysmic event at cosmological distance. A polite academic way of saying, "This might be something huge, please don't laugh." But something in the data refused to go away. The dispersion pattern was unmistakably extragalactic. The brightness was extraordinary. The frequency sweep was textbook clean. Slowly, quietly, the idea grew. This might be real, but science moves cautiously. One detection is fascinating, but not transformational. A single strange pulse wasn't enough to build a theory around. The Lorimer burst hovered in scientific limbo, too intriguing to ignore, too lonely to embrace fully. For a while, it became the radio astronomy equivalent of a campfire story. Something weird that might have happened. Maybe extraterrestrial interference. Maybe a magnetar outburst. Maybe a glitch in the instrument. Maybe something else entirely. But then the key question emerged. If this was real, where were the others? Radio telescopes scanned, searched, recalibrated. Years passed. Nothing. The Lorimer burst remained a ghost, haunting, unexplained, solitary. And then, in 2013, everything changed. More bursts began appearing. Not one, not two, but a handful, each with the same bizarre characteristics, bright, millisecond-long, highly dispersed, and coming from well outside the Milky Way. Suddenly, the Lorimer burst wasn't a curiosity. It was the first clue. Astronomers realized they had stumbled onto an entirely new category of cosmic phenomenon, something the universe had been doing for billions of years, but humans had never noticed until a graduate student dug through old data for a class assignment. The discovery of that single pulse permanently changed the landscape of radio astronomy. It opened a new field overnight. It forced telescopes around the world to upgrade their data systems, to scan more quickly, to search more deeply. It inspired new observatories, new theories, new missions. Entire careers launched from that one lonely spike in the noise. Today, thousands of FRBS have been catalogued. We know they are common, extremely common. We now believe that somewhere in the sky, once every second, a fast radio burst is going off. But in 2007, there was just the one. One burst buried in an old archive. One pulse crossing billions of years to reach a telescope that wasn't even pointed in the right direction out of purpose. Just chance. One whisper that started a scientific revolution. The universe had spoken. It simply took us 6 years to notice. For a moment, it seemed as though fast radio bursts had opened a door to something extraordinary. Cataclysmic explosions, extreme physics, perhaps even exotic astrophysical objects no one had ever imagined. But then, not long after the Lorimer burst gained fame, something strange began happening at Parkes Observatory. The telescope started picking up more bright, millisecond bursts, but these felt wrong. They were too frequent, too conveniently timed, too Earth-like in a way that made astronomers uncomfortable. The way a biologist feels uncomfortable when a new species turns out to be someone's escaped pet hamster. The signals were bright, dispersed, and eerily similar to the Lorimer burst, enough to raise eyebrows. But their properties didn't quite match what you'd expect from a signal travelling across billions of light years. Something was off. The dispersion looked almost correct, but not quite. The bursts seemed to cluster around mid-morning and early afternoon, and suspiciously, they always came from the general direction of the observatory itself. By 2011 and 2012, these strange events had gained a name. Perytons, named after a mythical creature said to cast a human shadow despite appearing as an animal, an elegant metaphor for something that looks cosmic but carries the distinct fingerprint of Earth. The problem was this. Perytons mimicked FRBS just well enough to be confusing. If FRBs were the universe whispering, peritons were like a prankster whispering through your window pretending to be a ghost. Astronomers were baffled. Were these signals real? Were they cosmic? Or were they the electromagnetic equivalent of someone saying boo? The Parkes team began a deep investigation. They questioned everything: cables, hardware, atmospheric effects, electrical storms, nearby power lines, wildlife, even cosmic rays striking the electronics. Nothing fit perfectly. Then came the suspicion nobody wanted to voice. What if it wasn't the universe at all? What if it was us? The possibility was almost embarrassing. Parkes is one of the world's most respected radio observatories. To mistake a kitchen appliance for a cosmic phenomenon would be the scientific equivalent of mistaking your own hand for Bigfoot in a blurry photo. But the clues began to line up. The bursts often appeared during staff lunch hours. They never occurred late at night. They tended to show up when someone was working in the main building, and most telling of all, the frequency pattern of the peritons wasn't identical to an FRB. It was stretched, distorted, subtly smeared in a way that pointed toward a very human kind of interference. Still, no one could quite figure out what human activity was causing them. Then, in 2015, during yet another investigation, someone had an idea. What if the interference wasn't coming from inside the telescope equipment, but from somewhere else on the grounds? So the team set up radio monitors around the site to catch the exact origin of the next periton, and eventually, during a routine lunchtime scan, the detector outside the building lit up. The source was not mysterious, not cosmic, not exotic. It was the observatory's staff microwave oven, not while heating food, interestingly, but when someone impatiently opened the microwave door before the timer finished. This action, interrupting the magnetron cycle, emitted a tiny burst of radio waves in exactly the frequency range Parkes was searching. A perfect little millisecond pulse. Warm leftovers wrapped in cosmic disguise. The astronomers were stunned, then they laughed, then they winced. It was a moment that perfectly captured the delicate nature of radio astronomy. The universe is full of breathtaking phenomena, but so is your kitchen. The revelation of the peritons didn't debunk the Lorimer burst or the other genuine FRBS detected later. Instead, it sharpened the methods used to tell real signals from imposters. It taught astronomers to be suspicious, even of beautiful data. It forced observatories worldwide to adopt stricter controls, cleaner instrumentation, and more rigorous protocols. And perhaps most importantly, it reinforced one of the quiet truths of science. Humility is not optional. You cannot assume that the universe is handing you a miracle. You must first rule out the possibility that someone is reheating their lunch. The scientific community took the lesson seriously. Chime, askap, meerkat, and other advanced telescopes were designed with redundancy to avoid human-made interference. Algorithms were rewritten. Cross-site confirmations became mandatory for unusual signals, and the field matured. It's easy to laugh at the microwave story now. Astronomers sometimes joke about putting "do not open early" signs on microwaves near telescopes, but it was an important moment. It safeguarded the credibility of FRB research and sharpened the tools that would later lead to monumental discoveries. Peritons were not embarrassments, they were reminders. Reminders that the universe is subtle, and so must we be. Reminders that noise can masquerade as beauty. Reminders that sometimes the hardest part of exploring the stars is filtering out the echoes of our own world. And once the static of Earth was cleared away, the real cosmic whispers began to emerge, clearer, stranger, and far more powerful than anyone expected. If you were to look at the raw data from a fast radio burst, you might think it looks like static, just a sudden bright streak across a waterfall plot of frequencies, but hidden inside that streak is a story written not in letters or symbols, but in delays, slopes, and microscopic hesitations, a story about everything the burst passed through on its way to us. To understand FRBS, you have to understand dispersion, the subtle stretching of the signal as it travels through the cosmos. It begins with a simple truth about radio waves. Not all frequencies move through plasma at the same speed. Higher frequencies slip through more easily, while lower ones lag behind, slowed by interactions with free electrons floating between stars and galaxies. So when a burst of radio waves travels across the universe, the high-frequency portion arrives first, clean, sharp, punctual, while the low-frequency tail drags behind, like the echo of a footstep in a long hallway. On a graph, this delay creates a downward sweep, a sloping diagonal line. It's beautiful in its simplicity, and it's loaded with meaning. Astronomers call the total amount of this delay the dispersion measure, or DM. DM tells us how many electrons the signal encountered along the way, how much stuff lies between the source and Earth. You can think of DM as the cosmic equivalent of counting raindrops. Not the raindrops that fall on your skin, but every raindrop in every cloud between your house and the horizon. FRBS allow us to measure the invisible. And the universe, it turns out, is full of invisible things. Between galaxies lies the intergalactic medium, a sparse ocean of ionized hydrogen and helium, incredibly thin, incredibly cold, and almost impossible to detect directly. Even its name feels unsure of itself. Medium. Not quite something, not quite nothing. But FRBS feel it. Every one of them, every free electron nudges the burst ever so slightly, slowing part of it down, and by the time the FRB reaches Earth, that tiny cumulative effect, spread over millions or billions of light years, becomes a readable fingerprint. When astronomers inspect that fingerprint, they're able to do something astonishing: count electrons across the universe, not in a vague, approximate way, literally measure the number of electrons between us and the source galaxy. Before FRBs, this was nearly impossible. The universe's missing baryon problem puzzled scientists for years. Models predicted more matter than telescopes could observe. It wasn't in galaxies, it wasn't in stars, it wasn't in gas clouds. Somewhere, a huge fraction of normal matter, ordinary protons and neutrons, was missing. But FRBS began solving that mystery, because when you compare the DM of an FRB to the expected contribution from its home galaxy and the Milky Way, the leftover dispersion can only come from one place: the invisible filaments of intergalactic plasma connecting galaxies. Suddenly, we could weigh the cosmic web. FRBS became probes, tools, lanterns shining through the fog. Imagine releasing a pulse of sound across the ocean, then determining every temperature change, every current, every density shift just by listening to how the echo stretches and warps. FRBS let us do that. But on the scale of the universe, dispersion also allows scientists to estimate how far away an FRB is before they ever see its host galaxy. A high DM often means a distant burst, though the universe is messy enough to add uncertainties. Some galaxies are thick with electron-rich environments that boost the dispersion. Others are pristine. Some FRBs pass through the halos of multiple galaxies. Some slip through cosmic voids. Every burst is a different journey. Every journey leaves a different signature. And so FRBS have become, in a way, cosmic weather reports. They tell us how turbulent the space between galaxies is, how magnetized it is, how dense the plasma is in different regions of the cosmic web, whether galaxies have thick halos of ionized gas or thin, diffuse ones, whether intergalactic filaments are smooth or clumpy. Every FRB is like a tiny probe sent across unimaginable distances, sampling the universe as it passes through it and delivering the data to us in one blisteringly fast flash. We don't get to choose where these probes go. We don't get to steer them or guide them. We simply listen when they arrive. And they arrive with secrets. The dispersion measure is the FRB's diary entry, documenting every step of its cross-universal journey. If you understand how to read it, you can reconstruct the invisible road the burst travelled. For decades, astronomers mapped the universe by looking at what glows: stars, galaxies, nebulae. But FRBS let us map what doesn't glow. what hides, what drifts between galaxies, forming the scaffolding of the cosmos. With each new detection, we gain a better sense of the universe's weather, its storms of charged particles, its breeze-like plasma flows, its long strands of diffuse matter stretching across millions of light years. And slowly, through these whispers, the universe reveals itself. Not in loud, dramatic declarations, but in the faintest delays of a radio wave, the most delicate tilting of a line in a plot of frequencies. Sometimes the most powerful discoveries hide in the static. For years after the Lorimer burst, astronomers believed fast radio bursts were one-off events, cosmic accidents so violent that whatever produced them didn't survive long enough to do it again. A burst, then silence, a single cosmic scream, a star dying, a collision, something catastrophic and final. It made sense. How could an event that unleashes the energy of days of sunlight in a millisecond happen twice? The universe, however, has a habit of humbling our assumptions. In November 2012, while scanning the sky with the Arecibo Observatory, the massive, bowl-shaped telescope nestled into the mountains of Puerto Rico, astronomers recorded a bright millisecond-long radio pulse. In isolation, it didn't look unusual. FRBs were still rare, but by then scientists had seen a handful. The burst was logged, analysed and stored, but Arecibo kept listening, and on May 20th, 2014, it heard another pulse, from the exact same spot in the sky, with the same bizarre dispersion measure, the same telltale curve in the data, the same cosmic signature. This shouldn't have happened. FRBs, according to the prevailing theories, weren't supposed to repeat. The object was named FRB121102, a dry catalogue label hiding what would become one of the most important discoveries in modern astronomy. The universe was repeating itself. Then came the third burst, and the fourth, and the 10th, and then dozens more. FRB121102 wasn't whispering, it was speaking, again and again, sometimes softly, sometimes violently, sometimes months apart, sometimes multiple times in a single minute. This single object changed everything. It was as if the cosmos had been sending postcards saying, "I'm alive," long after everyone assumed the sender was gone. Astronomers raced to pinpoint its location. Arecibo's giant dish gave rough coordinates, but not enough precision to locate the host galaxy, so an international effort mobilized. The Very Large Array in New Mexico, the European VLBI network, and eventually a global mosaic of radio dishes working together like a planet-wide ear. In early 2017, after months of triangulation, the source was finally identified, a faint dwarf galaxy more than 3 billion light-years away, a tiny, irregular galaxy forming stars at a furious rate. And in that galaxy, FRB121102 lived inside something even stranger, a constant, glowing radio nebula, an environment of extreme energy, like a stellar nursery or a turbulent magnetized region around a young neutron star. Suddenly, FRBs had personalities. Some were one-time events, some were restless, repeating over and over, some fired in clusters, some were silent for months, some followed patterns, some broke them. It was as though the sky had developed characters, voices with different temperaments. The discovery of the repeater shattered the idea that all FRBs come from catastrophic events. If an object bursts repeatedly, then whatever creates those blasts must survive the process. It forced scientists to rethink the entire field. Repeating FRBs pointed toward magnetars, highly magnetized neutron stars, as prime suspects. Magnetars are known to produce flares, eruptions, and magnetic quakes that could generate repeated bursts of energy. Meanwhile, non-repeating FRBs still behaved like one-off cataclysms, neutron star collisions, black hole interactions, or other terminal cosmic events. For the first time, scientists had to accept a new possibility. FRBs might not be a single phenomenon at all. They might be a family, a population, a spectrum of cosmic events sharing the same basic signature, but arising from wildly different physics. Some researchers proposed that repeating FRBs might come from young magnetars inside active star-forming regions, while non-repeaters could come from older, quieter galaxies where violent stellar births are rare. Others suggested completely different mechanisms: plasma lensing, orbital interactions, binary companions, or even cosmic string cusps snapping in space-time. And yet, with all these theories, one truth stood out. Repetition meant memory. Repetition meant endurance. Repetition meant a voice that wasn't silenced after its first cry. FRB121102 became almost a character in its own right. Mysterious, persistent, unpredictable. Its outbursts varied in intensity and structure. Sometimes it flashed with sub-millisecond microbursts nested inside the main pulse, like the cosmic equivalent of a heartbeat trembling inside a shout. It was alive in a way no one expected a cosmic phenomenon to be. And in a poetic sense, repeating FRBs feel more human, don't they? A single outburst could be anything, but a repeating one feels intentional, even though we know, scientifically, it isn't. There's something about hearing a voice more than once that creates a sense of closeness, recognition, familiarity, even trust. Repetition is how humans learn each other, how we form patterns, how we understand. The sky, in its own indifferent way, offered us a pattern. Repeating FRBs remind us that not everything in the cosmos is a one-time spectacle. Some things echo, some things persist, some things announce their presence again and again, daring us to listen more carefully. And because of FRB 121102, astronomers began looking for repeaters everywhere, and they found them. Many of them. Some quiet, some loud, some sporadic, some rhythmic, some almost musical in their patterns. Each repeating source is a reminder that the universe isn't just shouting randomly into the void. It has rhythms, some violent, some delicate, hidden inside the noise. Some voices speak only once, others speak many times. And both have stories worth hearing. If repeating fast radio bursts hinted that something in the universe could survive its own violent outbursts, then magnetars became the prime suspects almost immediately. They are the drama queens of astrophysics. Explosive, unpredictable, and outrageously powerful. And if the cosmos has a habit of putting extreme ideas into physical form, magnetars are among its favourite creations. A magnetar begins its life in chaos. It forms from the collapsed core of a massive star, one that lived fast, burned bright, and ended in the cataclysm of a supernova. What remains is a neutron star, a city-sized sphere with more mass than the sun crammed into a ball the width of Manhattan. Just that alone is already bizarre. But a magnetar is a neutron star taken to a physical extreme, endowed with a magnetic field so intense it seems like a joke nature is playing on us. To get a sense of scale, consider this. Earth's magnetic field, about 0.5 Gauss. A fridge magnet, 50 Gauss. A medical MRI machine, 10,000 Gauss. A magnetar, 10 to the power of 15 Gauss. 1 quadrillion times stronger than Earth's field, strong enough to distort atomic structures, strong enough to tear electrons from nuclei, strong enough that if you were within 1,000 kilometers, the magnetic field would scramble the electrons in your atoms and, well, you wouldn't be you anymore. These objects are as close to magic as physics allows. Their crusts can crack under magnetic stress, releasing titanic amounts of energy. Their magnetic fields can twist, snap, and reconfigure themselves like cosmic rubber bands. When they do, they unleash flares so intense they can affect satellites across the galaxy. For years, magnetars were considered a leading explanation for at least some FRBs, especially the repeating ones. Their behaviour, violent, sporadic, bursting, fit the pattern. But there was a problem. All confirmed FRBs had come from other galaxies, and magnetars in our own Milky Way, while energetic, had never produced anything like an FRB. Astronomers needed proof. A smoking gun, a galactic FRB. That moment arrived in one of the strangest years humanity has collectively lived through, 2020. While the world was distracted by earthly uncertainties, something extraordinary happened in space. On April 28th, multiple telescopes around the world detected a burst of radio energy unlike anything seen before. It was bright, sudden, unmistakably FRB-like. But this time, the signal wasn't from billions of light-years away. It came from inside our own galaxy. The source was SGR1935+2154, a known magnetar roughly 30,000 light-years from Earth. A magnetar we had studied before. A magnetar that occasionally behaved badly but had never done this. The burst, now called FRB200428, was historic. For the first time, the universe offered a direct connection between a magnetar and an FRB-like event. The signal wasn't as bright as the extragalactic FRBs we usually detect. Those are monstrously powerful. But FRB200428 was far brighter than any radio burst ever seen from a galactic source, enough to confirm the link, enough to prove that magnetars are indeed capable of producing FRBs, enough to shift the entire field forward. And the timing made it even more compelling. Just milliseconds after the radio burst, space-based X-ray telescopes detected a massive X-ray flare from the same magnetar. Two messengers from the same event, two windows into the violence of a magnetar's magnetic tantrum. This coincidence wasn't luck, it was physics. A magnetic quake, a crustal fracture, a sudden rearrangement of the star's monstrous field. Whatever triggered it produced both signals in nearly the same instant. Suddenly, the idea that magnetars might be responsible for at least a subset of FRBs became far more than speculation. It became evidence. Astronomers around the world celebrated. Not because the mystery was solved, far from it, but because a piece of the puzzle finally fell into place. Theories that once sounded bold or borderline speculative now had observational support. FRB 200428 showed that magnetars can produce FRB-like bursts. Their magnetic eruptions can generate both radio and X-ray energy. These bursts can be astonishingly bright, especially in younger, more active magnetars. This last point matters because the magnetar in our galaxy that produced FRB 200428 is old and relatively calm. If an aging mellow magnetar can produce a signal detectable across the galaxy, then imagine what a young hyperactive magnetar in a star-forming dwarf galaxy could produce. It would be far brighter, far more energetic, and easily visible across billions of light-years, which is precisely what FRB surveys observe. The connection became clear. Extragalactic FRBs were likely the result of magnetars in their youth, freshly formed from supernovae, volatile, magnetic fields twisting violently, bursting unpredictably. This didn't explain every FRB. Some are too bright, too extreme, too strange. Some behave too regularly, some occur in unexpected environments, but magnetars explain many of them, perhaps most, and they fit beautifully with what we know about repeating FRBs, their tendency to cluster, their variety, their unstable behavior. The universe rarely hands us certainty, but FRB 200428 was a rare cosmic nod. A yes in the middle of the static. It reminded us that sometimes the answers we seek in distant galaxies can be tested right here at home, and that even in a field as mysterious as FRBs, the path to understanding often begins with the simple act of listening quietly, patiently, to the universe's magnetic heartbeat. The magnetar connection may be the strongest thread we've uncovered so far, but the universe is not in the habit of giving us only one explanation for anything FRBs behave too differently, too strangely, too inconsistently to be the product of a single cosmic engine. Some of them look like the violent hiccups of newborn magnetars. Others look nothing like magnetar activity at all. And so the search widens, stretching from the familiar to the astonishing, from the solidly physical to the delicately hypothetical. Before magnetars stole the spotlight, pulsars were the reigning celebrities of radio astronomy. These rapidly rotating neutron stars emit beams of radio light with clockwork precision, sweeping space like cosmic lighthouses. When they glitch or flare, their beams can briefly spike in intensity. Occasionally, one of these spikes looks suspiciously FRB-like. Sharp, bright, narrow pulsars can misbehave. They can burp, they can surprise. But even their wildest moments rarely approach the sheer ferocity of an FRB from a distant galaxy. Pulsars are controlled. FRBs are unruly. Pulsars tick. FRBs explode. They share a family resemblance, but the resemblance fades when the numbers come out. Some FRBs, particularly the one-off, never-to-be-seen-again flashes, seem to hint at something far more catastrophic. Imagine two neutron stars spiraling into each other, swirling in a dance lasting millions of years, only to collide in a final instant with unthinkable violence. This process produces gravitational waves, ripples in the fabric of space-time, and a short gamma-ray burst. It also produces shock waves of plasma, relativistic jets, and electromagnetic fireworks. The very last instant of such a merger could, in principle, generate a millisecond radio flash, sharp enough to look like an FRB. If that's true, then some of the single bursts we've detected could be the dying breath of binary neutron stars. But mergers are rare. FRBs are common, far too common for all of them to come from such dramatic endings. If neutron star collisions are involved at all, they might only explain a tiny fraction of the brightest one-offs, those brief blinding bursts that almost rewrite the scales on detectors. And then, at the fringe of physics, lies a far more exotic possibility: cosmic strings. These hypothetical defects in space-time, infinitely thin, immeasurably long, are relics predicted by some early universe theories. If a loop of such a string formed and then snapped, or if two segments intersected, the event could, in theory, unleash a flash of energy so intense and so brief that it would resemble an FRBA momentary tear in the fabric of reality, a crackling ripple from the dawn of the universe reaching us billions of years later. It's a beautiful idea. It's also entirely unproven. Cosmic strings live squarely in the space between imagination and mathematics. They haven't been observed directly, and FRBs, tempting as they are, haven't provided the decisive evidence needed to move cosmic strings from theory to reality. Still, science allows the possibility to remain open, as long as imagination doesn't outrun the data. Black holes also linger in the conversation, not the silent, devouring monsters of popular imagination, but the environments around them: swirling accretion disks, turbulent magnetic fields, tangled plasma jets. These regions can twist space, accelerate charged particles to near-light speeds, and spark electromagnetic bursts. A sudden reconnection event near a black hole's magnetosphere, a shock wave in a relativistic jet, or a collapse in a plasma stream could flash a pulse of radio energy sharp enough to look like an FRB. Some bursts have indeed been traced to galaxies with active black holes, hinting that at least a handful may originate near these cosmic engines. But most FRBs lack the broader electromagnetic signatures you'd expect from black hole-driven chaos. And then there's plasma itself, the universe's favourite medium. In some FRBs, the burst structure is astonishingly complex. Sub-bursts stacked inside sub-bursts, microsecond modulations, echoes that look like reflections inside a cosmic hall of mirrors. These strange patterns may emerge not from the source, but from the journey, shaped by clouds of plasma acting like natural lenses. A faint FRB passing behind a turbulent plasma sheet could be magnified hundreds of times. A smooth burst may become jagged. A single pulse may split into several. Nature, with no intention at all, creates a cosmic light show. Some of the wildest FRBs, those with structures so intricate they look engineered, may simply owe their beauty to the lensing effects of plasma near the source. If you've ever seen sunlight flickering on the bottom of a swimming pool, you've already seen plasma lensing at work. It just looks far more dramatic on the scale of galaxies. The delicate balance in all of this is scientific discipline. FRBs are so strange and so diverse that it's easy to imagine exotic explanations for every burst. But astronomy thrives on restraint. Too little imagination and new physics goes unnoticed. Too much, and everything becomes a cosmic string or an alien beacon. The truth likely lies in a spectrum, magnetars explaining many FRBs, mergers explaining some, plasma lensing shaping others, and perhaps, just perhaps, the exotic theories contributing a rare spark here and there. The universe rarely uses one tool when it can use a handful, and FRBs, with their chaotic variety, remind us that the universe doesn't owe us simplicity, only truth, revealed slowly, flash by millisecond flash. Finding a fast radio burst is easy. Finding where it actually came from is something else entirely. A burst that lasts 1,000th of a second disappears almost before the telescope even knows it happened. By the time researchers realize they've captured one, the signal is long gone. No afterglow, no trail, no glowing debris cloud, just a crisp spike in a data stream. It's like hearing a single sharp sound in a vast forest at night and trying to deduce not only which direction it came from, but which tree branch snapped. Early telescopes such as Parkes and Arecibo could hear FRBs with remarkable sensitivity, but their vision was hopelessly blurry. They could detect a burst with pinpoint intensity, yet couldn't say exactly where in the sky it originated. A region the size of the moon was considered a good estimate. But in a space that large, there are thousands, or tens of thousands, of galaxies. Trying to identify the host of a lone FRB felt like trying to identify which firefly in a swarm blinked once and then vanished. Everything changed with the rise of interferometry. Instead of relying on a single dish, interferometric arrays use many antennas spread across large distances, sometimes across entire continents. Each antenna receives the FRB at a slightly different moment. Differences measured in millionths or even billionths of a second. When these signals are combined, the time offsets allow astronomers to reconstruct the direction of the burst with astonishing precision. Where a single dish might only narrow the location to a large patch of sky, an interferometer can shrink that patch to a point smaller than a galaxy, sometimes even to a single star-forming region within it. It's similar to how your two ears let you determine the direction of a sound. Except instead of two ears a few centimeters apart, imagine dozens of ears spaced kilometers or thousands of kilometers apart. The Australian SCAR Pathfinder, better known as askap, became one of the first major breakthroughs. Scattered across the Western Australian desert, its antennas can scan huge areas of sky with advanced phased array feeds, catching FRBs in real time. And unlike earlier detectors, askap could immediately calculate their precise positions. Suddenly, an FRB was no longer an anonymous cry from the cosmos. It had an address. Some bursts were traced to galaxies brimming with new stars, some to tiny dwarf galaxies glowing faintly on the edge of detectability. Some came from regions dense with young, massive stars, others from quiet, elderly galaxies where star formation had long burned out. Localization transformed FRBs from mysterious flashes into astrophysical specimens. Then came chime, an instrument that doesn't look like a telescope at all. Instead of round dishes, chime uses 4 long, stationary, curved cylinders, like giant metal troughs, resting in a Canadian valley. It doesn't track the sky moves over it as Earth rotates. This simple but ingenious design allows chime to monitor enormous portions of the sky continuously, detecting FRBs by the hundreds. While chime's localization abilities are less sharp than askap's, its detection power is unmatched. What chime can do is alert the world. A burst happened here, right now. Point your fancy arrays at this region, quickly. And when interferometers join in, arrays like the Very Large Array in New Mexico or global networks using VLBI techniques, the rough position becomes precise. Sometimes, astonishingly so, a burst that lasted less than your blink suddenly acquires a home galaxy, a star-forming knot, a local environment. This is where the story becomes even more interesting. Because once you know where an FRB came from, you begin to understand what produced it. Several localized FRBs point to dwarf galaxies with intense star formation, galaxies filled with massive stars that live fast and die violently, often leaving behind magnetars. This environment makes magnetars an especially strong candidate for many FRBs. But other FRBs come from large, quiet galaxies where new stars are scarce. The source in those cases may not be a young magnetar at all. Maybe an older magnetar still capable of occasional outbursts. Maybe something more exotic. A few bursts appear close to galactic centers, regions dominated by dense star clusters and supermassive black holes. The physics there is intense. Magnetic fields twist violently, plasma flows chaotically, and gravity behaves like a sculptor caught mid-stroke. An FRB from such a place hints at processes we barely understand. And then there are the odd FRBs found in the outskirts of galaxies, lonely places where there's little ongoing star formation. These events raise eyebrows because they challenge the idea that magnetars alone can explain everything. Every pinpointed FRB adds a new puzzle piece. Every host galaxy adds texture to the mystery. Every environment tells a different part of the story. What once seemed like random flashes from nowhere are now part of a cosmic atlas. We can map them, we can count their homes, we can study their neighborhoods, and slowly, FRB by FRB, the universe reveals the places where its most fleeting explosions are born. Somewhere, as arrays across the planet continue listening, askap in the desert, chime in the mountains, interferometric networks stretching across continents, another burst is already racing toward us, a millisecond flash, carrying clues about the galaxy that released it. All we have to do is catch it and trace that whisper back to the place it was born. In the middle of a quiet Canadian valley, surrounded by forested hills and long winters, sits one of the strangest telescopes ever built. It doesn't look like a dish, it doesn't tilt, it doesn't rotate, it doesn't turn its gaze across the heavens like traditional observatories. In fact, it doesn't move at all. And yet, this immobile machine sees more fast radio bursts than any other telescope on Earth. Its name is CHIME, the Canadian Hydrogen Intensity Mapping Experiment, and if FRBS are the universe's millisecond whispers, then CHIME is the universe's biggest set of ears. The design is deceptively simple. 4 enormous metal cylinders stretch across the ground like half pipes from a forgotten skate park. They're fixed in place, pointing straight up at the sky, letting Earth's rotation do the work of scanning the heavens. As the planet turns, the sky passes overhead, and CHIME watches everything that moves across its elongated field of view. No motors, no gears, no swiveling platforms, just geometry and gravity working together with a remarkable network of electronics. Because CHIME never moves, it never blinks. And because it never blinks, it catches things other telescopes almost always miss. Every day, as Earth spins eastward, CHIME scans a massive slice of the sky, thousands of square degrees, without pause. In one 24-hour rotation, it observes a swath so wide that it effectively monitors the entire northern sky. It's like having a security camera pointed upward, recording every flash, every flicker, every unusual burst of cosmic activity, 24 hours a day. This constant surveillance turned CHIME into a revolution. Before CHIME, astronomers detected FRBS in 1s and 2s, rare jewels found by chance, requiring luck and long hours of silent listening. But CHIME changed the rules. It didn't hunt FRBS. It intercepted them. It caught them by the dozens, then the hundreds, then the thousands. Suddenly, the field shifted from scarcity to abundance. The FRB catalogue exploded. Every week brought new detections. Patterns started to emerge. Anomalies demanded explanations. The statistical fog that had shrouded FRBS since the Lorimer burst began to lift. It was no longer about finding FRBS one at a time. It was about understanding their population as a whole. The instrument's power comes from its unique design. While traditional radio dishes concentrate signals into a single high-sensitivity beam, chime uses digital beamforming to create hundreds of overlapping beams in real time. It's like having many eyes looking in slightly different directions, all simultaneously scanning the sky. If an FRB fires anywhere within that enormous field of view, chime registers it. A burst that lasts less than a millisecond isn't a problem for a machine that never looks away. One of chime's most remarkable achievements was the discovery of repeating FRBs on a massive scale. Before chime, repeaters were rare curiosities, sources like FRB 121102 that blazed again and again from distant dwarf galaxies. But chime revealed that repeaters might not be the exception at all. They might be part of a broader family. It detected dozens of repeating sources. Some repeated frequently, some only occasionally. Some showed bursts clustered in tight groups, followed by long periods of silence. Some revealed strange periodicity, a pattern chime was uniquely suited to detect. One FRB source even showed a 16-day cycle of activity, bursts for a few days, then nothing for nearly 2 weeks, then bursts again. Without chime's continuous monitoring, that pattern would have been invisible, lost in the gaps between observations. Then came another surprise chime discovered, FRBS, that burst in substructure, tiny microbursts sitting inside the main burst like nested echoes. Some displayed upward drifts in frequency, some downward drifts, some complex interference-like patterns. Observers saw fine details that had been invisible in earlier detections simply because chime recorded events constantly and in high-time resolution. The telescope didn't just find more FRBS, it found richer FRBS, more varied, more complex, more alive. But perhaps the most important contribution lies in the statistical goldmine chime created. With thousands of events logged, astronomers could finally study FRBS as a population, not just as individual oddities. Patterns emerged that were impossible to see when we only had a handful of detections. One of the first insights was distribution. FRBs are not clustered in one region of the sky. They appear everywhere, uniformly, suggesting their origins are cosmic and widespread rather than local. They are not tied to the Milky Way. They are not artifacts of human activity. They are not rare. If anything, they are incredibly common, perhaps happening somewhere in the universe every second. Another insight came from brightness and frequency patterns. FRBS follows statistical distributions similar to earthquakes and solar flares. Many small ones, fewer big ones. This correlation hinted that FRBS might emerge from systems capable of releasing energy in unstable bursts, systems like magnetars, which naturally produce sporadic flares of different magnitudes. Chime also uncovered unusual frequency-dependent behaviors. Some FRBs prefer lower radio frequencies, ringing like deep cosmic bass notes. Others show narrow bands, like whistling tones. Some sweep smoothly downward in frequency. Others scatter and flicker as they pass through turbulent plasma. These variations gave astronomers new tools to probe the environments around the sources. Then came the geographical distribution across galaxies. Localization studies, often done in partnership with interferometric arrays, revealed the galaxies hosting these bursts. When chime found a new source, follow-up observations often narrowed it down to a region of intense star formation, a dwarf galaxy, or sometimes an older, calmer galaxy. Each environment added nuance to the developing picture of what FRBS truly are, but it doesn't stop there. Chime continues to run, day after day, night after night, swallowing vast amounts of data, catching every FRB bright enough to reach it. It sees the patterns we don't expect. It sees the quiet whispers between the loud ones. It sees the faintest anomalies that hint at physics not yet understood. The telescope has become a kind of census taker for cosmic flashes, a keeper of the universe's fleeting sparks, a patient archivist cataloguing every burst, every whisper, every millisecond shout that races across space. And the more it listens, the clearer it becomes. FRBs are not rare cosmic accidents. They are woven into the fabric of the universe. They are happening all the time, everywhere, in galaxies large and small. The sky is alive with them. Chime simply taught us how to hear. For all their mystery, fast radio bursts have become more than astronomical curiosities. They're tools now, unexpected instruments for exploring some of the universe's deepest questions. In a strange twist of cosmic irony, these millisecond flashes that once baffled astronomers have become some of the most powerful probes we have for studying the invisible structure of the cosmos. Every FRB is a messenger, carrying with it the imprint of everything it has passed through. And because they travel such immense distances, their signals accumulate tiny distortions, microscopic fingerprints left by the material scattered across billions of light years. To a casual observer, these distortions might look like static or noise, but to astronomers, they are data. They are the universe confessing its secrets in a millisecond blink. One of the biggest surprises hidden inside those blinks is the ability to track down something that had been missing for decades. Ordinary matter, not dark matter, not dark energy, just normal baryonic matter. The protons, neutrons, and electrons that we know make up stars, planets, gas, and people. For years, cosmologists had a problem. The early universe's composition could be calculated precisely from measurements of the cosmic microwave background and the ratios of light elements forged in the first minutes after the Big Bang. Those numbers predicted a certain amount of baryons should exist today. But when astronomers added up all the matter in stars and galaxies and gas clouds, nearly half of it was missing. Not exotic matter, not hypothetical particles, plain old protons. The prevailing theory was that the missing baryons weren't gone. They were simply spread thinly across intergalactic space, too diffuse to be seen directly. Like a mist so faint you can't see it when you look straight at it, only when a beam of light catches it from the right angle. FRBS provided that angle. When an FRB travels across the cosmos, its radio waves pass through this faint, ionized intergalactic matter. Every electron slows the lower radio frequencies by a tiny, tiny amount, add up billions of light years of electrons, and that delay, the dispersion measure, becomes measurable. FRBs allowed astronomers to trace how many electrons lie between us and the source. And when scientists began comparing those dispersion measures with what cosmology predicted, the numbers lined up. The missing matter wasn't missing at all. It was simply hiding in the liminal spaces between galaxies, spread across the cosmic web. FRBs illuminated it like flashlights sweeping through fog. Then came an even more ambitious idea, using FRBS to probe the expansion of the universe itself. As the universe expands, the space between galaxies stretches, dragging light with it. This expansion affects how radio waves propagate, just as it affects visible light. The farther away an FRB is, the more its signal is stretched and dispersed, not only by electrons, but by the geometry of space-time. If you can measure the dispersion accurately, and you know where the FRB lies, meaning you've identified its host galaxy and redshift, you can compare the amount of dispersion to the amount of cosmic expansion. In other words, FRBs offer an indirect way to measure the universe's growth, not as precise yet as supernova measurements or cosmic microwave background data, but dense with potential. With thousands of FRBS and good localizations, astronomers could refine the expansion rate, test cosmological models, and even probe slight variations in the density of matter across the universe. It's astonishing that something so brief could help decode something so vast. And then there's magnetism, the invisible sculptor of cosmic structure. Magnetic fields thread through galaxies, weave through the intergalactic medium, and guide the motion of charged particles on colossal scales. But magnetism is hard to measure at large distances. Light doesn't carry a simple signature of magnetic fields unless those fields twist or polarize it. FRBs, however, are so bright and so sharply polarized that even tiny rotations in their polarization become measurable. This effect, known as Faraday rotation, reveals how strong magnetic fields are along the FRB's journey. Some FRBs show enormous rotation, meaning they've passed through wildly magnetized plasma, perhaps near a galactic center or a magnetar. Others show very little rotation, hinting that their paths crossed quiet, diffuse regions of intergalactic space. By comparing these measurements across thousands of bursts, astronomers can begin mapping the magnetic architecture of the universe. Something once thought nearly impossible, FRBs are like compass needles thrown across the cosmos, each one tracing the invisible currents of intergalactic magnetism. It's hard not to feel a sense of awe in all of this. These bursts last less time than a blink, less time than a neuron fires, less time than it takes your thoughts to form, and yet each one carries more information than entire galaxies spread across the night sky. They are cosmic shortcuts, compressing vast distances into measurable clues. They are reminders that the universe often hides complexity inside moments so brief we almost overlook them. And they are the perfect paradox, the brightest events compressed into the shortest instants, revealing the largest scale structures. There is something poetic, even instructive in that, as though the universe, in its grand indifference, is teaching us that time doesn't dictate importance, that meaning doesn't require duration, that sometimes the most revealing phenomena are not the ones that burn longest, but the ones that flare brightly and vanish, leaving behind echoes rich enough to decode entire chapters of cosmic history. A millisecond is nothing to a human life, but to the cosmos, a millisecond can contain a map of the universe, and every time one of those flashes reaches us, travelling across unimaginable emptiness, it feels like the universe is sending a lesson, not in words, not in symbols, but in the language of physics, a language made of dispersion, rotation, brightness, and silence. A language we are only beginning to understand. The universe doesn't speak often, but when it does, its lessons arrive at the speed of light. Some fast radio bursts behave the way we expect them to, a single sharp spike, a clean sweep in frequency, a textbook dispersion curve, but others behave like they're trying to break the textbook entirely. These are the outliers, the extremes, the bursts that sit at the far ends of every distribution, the ones that make theorists sigh, tilt their heads, and open new tabs in their notes titled, "Okay, what is this?" The extremes are where FRBs become less like bursts of light and more like cosmic puzzles. A few FRBs arrive with dispersion measures so high they seem almost impossible. Dispersion is supposed to scale with distance. More electrons means a longer journey, a thicker path through cosmic plasma, but some bursts show dispersion values far beyond what their apparent distances should allow. When scientists look at these cases, the math whispers something strange. Either the FRB is unimaginably far away, or it passed through an environment so dense, so chaotic, and so full of ionized material that its path was like wading through cosmic fog. Some bursts carry dispersion measures so extreme that astronomers suspect they might come from galaxies packed with young, violent stars, or from the hearts of nebulae energized by newborn magnetars. Others may have passed through the turbulent magnetic cocoons surrounding supernova remnants, or the sizzling plasma around galactic centers. There's even speculation that some FRBs might be magnified by plasma lensing, with dense clouds acting like amplifying prisms that distort the signal. Whatever the explanation, these high dispersion bursts tell us something important. The universe contains pockets of astonishingly dense plasma, harsh, unkind environments where magnetic fields twist like tangled wires and electrons swarm like cosmic dust storms. But dispersion is just the beginning. Brightness is another axis where FRBs break all expectations. Many bursts detected by chime, askap, and other arrays are bright enough to outshine entire galaxies in that single millisecond. But then there are the ultra-bright ones, the FRBS, that appear to deliver energies so absurd that scientists reread the instrument calibration just to be sure nothing broke. There was a burst discovered in 2018 that was so bright the data saturated the detector. Another, with a dispersion measure near 2000, came from so far away that it should have been far too faint to detect, yet it arrived with a clarity that made observers question whether something had amplified it. Some FRBs appear to undergo natural magnification through gravitational lensing or plasma lensing, producing echoes or double-peaked structures that seem to violate causality unless you know the medium they travelled through. And then comes the truly strange part, when you zoom in. When you look at an FRB, not just as a burst, but as a structure in time, instead of being a single neat spike, many FRBS break apart under high-resolution analysis. They reveal subbursts, tiny flashes nested inside the main flash microstructure, measured not in milliseconds, but in microseconds or even nanoseconds. This means the physical processes behind these bursts are unfolding faster than neurons can fire, faster than muscles twitch, faster than your conscious mind can register anything at all. These subbursts are layered like delicate cosmic embroidery, fine threads revealing the turbulence of the environment near the source. Some FRBs show downward frequency drifts, each subburst arriving at a slightly lower pitch than the one before, like a cosmic slide whistle. Others flicker with interference-like oscillations, hinting at plasma lensing, or shock waves interacting with tangled magnetic fields. And some bursts split into multiple tracks, like radio lightning refracted through shifting sheets of plasma. One repeater in particular, FRB 121102, has shown microbursts separated by mere tens of microseconds. Think about that. Events separated by a fraction of the time it takes your brain to send a signal to your hand. To produce such sharp structure, the emitting region must be extraordinarily compact and the surrounding plasma environment unbelievably complex. These bursts are like strobe lights in the dark, revealing the messy, chaotic physics of magnetars or whatever extreme objects sit at the engines of these flashes. And then there are bursts that repeat with patterns so strange they feel almost rhythmic. Not organised rhythm, nothing like the steady ticking of a pulsar, but clustered flurries followed by long silences. It's as if some cosmic engine coughs out a chaotic chain of sparks, takes a breath, then fires again. Chime detected sources that burst dozens of times in a single hour, then go silent for months. One source followed a 16-day cycle, 4 days active, 12 days quiet. Predictable chaos. All these strange behaviours. The ultra-bright flashes, the extreme dispersion, the nanosecond substructure, point to one unavoidable truth. Whatever produces FRBs must involve physics at the absolute edge of what matter, magnetism, and plasma can endure. Magnetars fit that picture well, with magnetic fields 1 trillion times stronger than Earth's, and crusts that can crack with the force of 1 billion atomic bombs. But even magnetars struggle to explain the most extreme bursts, the ones that seem almost too bright or too structured to come from any known mechanism. Some theorists wonder whether the extreme FRBS require multiple mechanisms layered together, a magnetar cracking, plasma lensing amplifying the result, turbulent environments shaping the sub-bursts. Others suggest more exotic processes, bizarre magnetospheric interactions, or even objects not yet described in textbooks. No one knows for sure. What's certain is that these extreme FRBS push the limits of models, forcing scientists to rethink assumptions about neutron stars, plasma physics, and the environments where such events unfold. They stretch imagination and theory alike, blurring the line between known physics and whatever comes next. And beneath the science, there's something deeply poetic about these flashes. Events so powerful, so fast, so finely structured that they reveal physics occurring on timescales shorter than thought itself. The universe hides complexity inside moments so brief they almost don't happen at all, unless we listen with instruments fast enough and clever enough to catch the details. There's a reminder in that, quietly hidden in the microseconds. Important things don't need to last long. Some of the most extraordinary phenomena in the cosmos happen faster than our minds can comprehend, yet reveal truths big enough to reshape our understanding of the universe. The sky crackles with these millisecond miracles, and the more closely we look, the stranger and more beautiful they become. The story of fast radio bursts is still in its opening chapters. For all the progress made, the catalogues, the repeaters, the exotic theories, there is a sense that we've only learned to read the shadows of these events, not the events themselves. Every new burst seems to hint at deeper layers, deeper physics, deeper truths hiding under the static. And the next decade of FRB science promises something extraordinary: clarity. A new generation of telescopes is rising, and among them stands a project so vast it borders on surreal. The Square Kilometre Array, SCAR, is not one telescope, but a continent-spanning observatory stretching across South Africa and Australia. It will be the most sensitive radio array ever built, a machine capable of hearing whispers so faint they would have slipped beneath detection for all of human history. When a SCAR comes fully online, it will expand FRB science the way the Hubble expanded cosmology, quietly, steadily, and then all at once. SCAR will be able to detect FRBs far dimmer and farther away than anything current telescopes can see. It will find them at redshifts so distant we'll be listening to bursts occurring when the universe was young, when galaxies were first assembling themselves from clouds of hydrogen. These ancient FRBs will act as probes studying the early cosmic web, the birth of structure, the evolution of matter itself. For the first time, we may be able to map the universe's hidden architecture, not with galaxies or quasars, but with millisecond sparks flung across billions of years. But SCAR's true power isn't just sensitivity, it's timing. With hundreds of dishes spread across thousands of kilometers, SCAR will be able to triangulate FRBs in real time. That's something current arrays struggle to do. Today, when an FRB hits, astronomers often scramble after the fact, combing through data, performing painstaking correlations, hoping another telescope caught the same burst. With SCAR, that delay may vanish. A burst will arrive, multiple dishes will record it. The system will compute the tiny timing differences almost instantly. Within seconds, astronomers will know where on the sky it came from, sometimes with such precision that they can point optical and X-ray telescopes at the same galaxy immediately. Imagine hundreds of telescopes worldwide turning toward a single spot in unison because SCAR whispered, "Something just happened there." This real-time triangulation is one of the holy grails of FRB science. It means catching a burst as it happens, not after the echo fades. It means seeing whether the burst is accompanied by an X-ray flare, a gamma-ray flash, a gravitational wave, or something no one has predicted yet. If an FRB ever coincides with a gravitational wave signal, if the universe ever sends both a ripple in space-time and a millisecond radio flash from the same event, we'll be standing at the threshold of a new era of multi-messenger astronomy. And SCAR isn't alone. New instruments like Meerkat, the Deep Synoptic Array, and upgrades to existing arrays promise better resolution, faster processing, and deeper surveys. Chime itself is evolving into chime/FRB outriggers, a distributed network built to give the original instrument precise localization abilities. For the first time, we'll catch FRBs simultaneously from multiple continents, the way seismologists triangulate earthquakes. When that happens, patterns may begin to emerge, patterns we can't see yet. Some FRBs might hide periodicities, subtle rhythms buried under their chaotic bursts. We've already seen hints, the 16-day cycle detected by chime, and strange clustering behaviors in a handful of repeaters. Perhaps there are deeper cycles, long-term modulations tied to binary companions, magnetar rotations, precession, or environmental changes. Or maybe some FRBS follow statistical rhythms that reflect the physics of their engines, the way volcanoes or earthquakes follow distributions governed by physical stress. SCAR will look for these rhythms with a sensitivity unmatched by anything before it. If FRBs have patterns, whether in time, in strength, in polarization, or in the microstructure of their bursts, we will find them. But the most tantalizing possibility extends beyond the familiar boundaries of astrophysics. Some scientists believe FRBS could reveal cracks in the standard model, not because FRBS are exotic themselves, but because their extreme environments push matter and fields into regimes we've never observed directly. The densities near a magnetar's crust, the magnetic fields twisting through plasma clouds, the relativistic shocks that accelerate particles to near-light speeds. All of these are natural laboratories for physics that cannot be reproduced on Earth. By measuring the polarization of FRBS, the rotation of their electromagnetic waves, the strange microsecond patterns inside their bursts, and the way they interact with intergalactic plasma, scientists hope to look for slight violations of symmetry, exotic plasma effects, signatures of axion-like particles, hints of quantum electrodynamics under extreme magnetic fields, deviations from standard relativity in the propagation of radio waves. FRBs cross enormous distances. That alone makes them test particles for the geometry of space-time. If some tiny deviation exists, some subtle effect predicted by speculative physics, an FRB's signal may carry it. Every burst becomes a natural physics experiment, every millisecond an opportunity. As we move into this new age of FRB science, there's a quiet sense that something big is approaching. Not a single discovery, but a change in how we listen to the universe. FRBS began as anomalies. Then they became curiosities. Then patterns emerged. Then families. Then tools. Soon they may become foundational. In their brief lifetimes, shorter than a human blink, FRBs offer everything from measurements of missing matter to tests of fundamental physics. They illuminate galaxies, map cosmic magnetism, trace ancient plasma structures, and whisper clues about the universe's earliest epochs. There's a strange humility in that. We often look for answers in the loud, the bright, the dramatic. But the universe, it seems, prefers to speak in flashes so fast we once overlooked them entirely. The future of FRB science will not just be about collecting more bursts. It will be about understanding what those bursts really are, what engines power them, what environments shape them, and what deeper truths they carry. It will be about listening carefully to some of the shortest events in the universe, because inside them may lie some of the longest-standing mysteries. And as SCAR rises, as worldwide arrays synchronize, as the sky becomes a laboratory of fleeting signals, we'll be ready to hear the next whisper when it arrives. There is something almost paradoxical about fast radio bursts. They are among the shortest events we can detect in the universe. Blinks of radio light so brief they barely exist in the way we understand existence. And yet, somehow, they open some of the deepest doors in modern astronomy. How do events that last 1,000th of a second end up teaching us about billions of years of cosmic evolution? How can something that comes and goes faster than thought carry information about everything between here and the edge of the visible universe? Maybe the answer is that brevity doesn't diminish meaning. Sometimes it sharpens it. When you listen closely to an FRB's signature, the sweep in frequency, the delicate slowing of its lower pitches, the imprints of every electron it encountered, you start to realize that these bursts are not simply flashes, they are conversations. Quiet ones, yes, but conversations nonetheless. The universe speaking in its own syntax of magnetism, plasma, turbulence, and time. We tend to associate wisdom with longevity, mountains, ancient trees, the slow drift of continents. These feel meaningful because they endure, but the universe doesn't share this bias. It doesn't care about duration. It hides its most astonishing physics inside instants too short to sense, too brief to experience, too fleeting to grasp without machines that monitor time with microsecond precision. If human perception was our only tool, we would never know FRBs existed. They are shorter than a blink, shorter than the time it takes sound to leave your lips, shorter than the interval between heartbeats. Our senses are simply too slow. The universe moves in tempos we weren't built to follow, but our instruments can. Our curiosity can. Our willingness to listen can. There's a quiet humility in acknowledging that most of reality passes too quickly for us to notice. That our experience of time, slow, steady, continuous, is only a tiny sliver of the cosmic spectrum. Stars evolve over billions of years, black holes grow over eons, galaxies collide in dances that unfold over epochs, and then there are FRBs, violent, tiny flashes that are over before the neurons in your brain could even fire the signal that something happened. The contrast is jarring. And yet, the universe embraces both extremes with equal ease. These bursts remind us that cosmic events don't need to be long to be significant. Some of the most revealing clues about the universe's structure come from analysing these ephemeral whispers. They carry maps of intergalactic matter. They trace the skeleton of the cosmic web. They encode the twists of magnetic fields in distant galaxies. They reveal the presence of magnetars so young and volatile that their surroundings glow with plasma storms. Inside a millisecond, an FRB can contain more information than we could gather from years of studying a quiet, ordinary star. It makes you wonder what else we're missing. What other flashes happen every day, too quick or too faint or too exotic for us to detect? How many conversations the universe is having without us? How many phenomena wait just outside our sensory limits, not because they are rare, but because we haven't yet learned how to listen in the right way? In a sense, fast radio bursts remind us that the universe is always talking, but it rarely talks loudly, and it rarely talks long. There is poetry in that, a kind of cosmic minimalism, a reminder that not everything worth hearing is stretched across time. When you think about it, our own lives are filled with moments like this, tiny instants that reveal something enormous, a decision made in one breath, a thought that changes everything, the whole arc of a life turning on a second of clarity or connection. We sometimes underestimate the power of brevity because we underestimate the power of attention. FRBs ask us to pay attention. In the quiet of a night sky, sitting beside radio telescopes that listen endlessly in the dark, there is a sense that these bursts are less like mysteries and more like punctuation marks, not sentences, not paragraphs, just small, sudden sparks that illuminate the text around them. And perhaps that's the most philosophical truth FRBs offer. The universe doesn't explain itself in long speeches. It leaves clues, flashes, hints, brief outbursts of information that we collect and interpret as best we can. The meaning is never in the duration. It's in the echo. As we come to the end of this journey, through magnetars, plasma storms, intergalactic fog, exotic physics, and strange repeating signals, there's a gentle reminder that science and wonder aren't opposites. They're companions. You can understand FRBs in technical detail and still feel something when imagining a millisecond burst crossing billions of light years to touch the edge of a human-made instrument on a rotating planet. These bursts aren't speaking to us, not in any intentional way, but there's something profoundly moving about being able to hear them at all, something comforting about knowing that even in the vast silence of the universe, there are still sparks, brief, bright, impossible sparks, reminding us that the cosmos is very much alive with hidden conversations. So take a moment to settle into the quiet. Let the mind drift over the landscapes we've explored. The cold edges of galaxies, the magnetic scars of neutron stars, the faint plasma drifting through cosmic filaments. Imagine those millisecond flashes travelling through all of it, untouched, unstoppable, carrying the signatures of everything they passed through. And as you breathe out, let the thought settle. The universe doesn't need time to be profound. It only needs a moment. Thank you for listening, for wandering through these brief but powerful cosmic sparks. Now, rest if you'd like. Let the mind soften, let the night wrap around you gently, and sleep well under a sky full of whispers.